Sanjay Nagarajan, and all the participants for this webinar on biogas-based refineries. When thinking about biotechnology, many people picture a scientist in a lab coat developing a life-saving drug or a medical device. While this image represents one common biotechnology career path, lab work is not the only option. With many exciting discoveries to make and new problems to solve, biotechnology professionals can make a difference in the lives of many other ways. I hope the participants will gain some valuable information about the new technology involved in the production of biogas and the career opportunities involved along with the industry. With these few words, I once again welcome you all for this webinar. Thank you.
I'm going to introduce the speaker at the moment. The speaker will be Dr. Sanjay Nagarajan. He did his undergraduation in Karpaka Vinayaka College like a few years ago along with me, and followed by his undergraduation, he did his master's in NUS Singapore and his PhD in Robert Gordon University and Queen's University, both in UK and both in UK. He also has an experience of working as a postdoc researcher in Birmingham City University and a research engineer in NUS. But currently, at the moment, he's working as a research fellow in Queen's University. He has experience. He has published more than 10 research papers at the moment. So far, at the moment, the thing is, he has been working on biofuels for the last 10 years or more from his undergraduate project. Because I'm one of his part of his project from all those moments. So I can assure you, I can tell you that he is a very good experienced person when it comes to biofuel. He is focusing on that biofuels for a long time now. He became very much mature at this moment. So I hardly thank for him to be here, spending his time here. So without further ado, I will ask him to do his presentation. Thank you, Sanjay, for being here.
Thank you, Hari, for the kind introduction. I will go into the presentation straight away. So the topic for today is going to be biogas-based biorefineries. I'm going to give an overview of what biogas and what biorefineries are. So to start off with, just trying to start the presentation here. Yeah, got it there. So we need to first think about what we need to do or why we need to do things. So in this context, I would like to take you through by giving you a quick introduction of what this is. So firstly, we know that there is global warming that's happening, which is because of greenhouse gas emissions. And greenhouse gas emissions are due to a lot of anthropogenic reasons. And firstly, if we take a look at the global sectors that contribute towards greenhouse gas emissions, we can see that the electricity sector and the transportation sector contributes to majority of the emissions. And greenhouse gases here, I mean specifically carbon dioxide. It can also be other gases like nitrous oxide, methane, and things like that as well. But everything is currently converted to a carbon dioxide equivalent, so it's on a carbon dioxide basis here. So if we see on a global scale, for electricity production and transportation, it is about a 60-odd percentage. But if we specifically take a look at what's happening in India, the carbon dioxide emissions are more in electricity sector, obviously, and the industrial sector. With India being a developing economy, it is inevitable that our industrial sector keeps growing. But this doesn't mean that we would need to keep emitting carbon dioxide. There is big scope of actually reducing the carbon dioxide emissions by also increasing or improving the industry itself. And again, the third contributing factor in India specifically is again transportation sector. So all these three combined are the major contributors of carbon dioxide in India. What is happening with these emissions is because of the use of fossil fuels for the production of energy, we tend to emit these carbon dioxide or other greenhouse gases. So what needs to be done is to determine an alternative fuel, and to determine an alternative fuel that suits the geography as well as cuts down the emission. It needs to be It needs to be determined on a case-by-case basis. So our current renewable energy alternatives are quite a few. So the first two being wind energy and solar energy. With wind energy and solar energy, the efficiencies are pretty much going up now, but the cost is actually immense, specifically with wind energy. With solar energy, the solar panels that you commonly know are nothing but the photovoltaic modules. These modules, the efficiencies have skyrocketed now. So the early 1990s, I think, was about 5% efficient. Now it's about 25% efficiency for solar panels. So with the efficiency going up, obviously the cost comes down. So the scope of getting a solar park done is actually much bigger. And recently, I think India has also inaugurated a 750 megawatt solar park. So these can actually take care of the grid electricity or supplements for grid electricity that we do now. But for transportation fuel specifically and for the gas sector, we would need to focus on biofuels. Why biofuels? Is because we've got bioethanol and biodiesel, which are alternatives for the transportation fuels. Bioethanol specifically for petrol. It could either be blended with petrol or it could be used as a fuel by itself. And then we've got biodiesel, which is an alternative towards petrodiesel or fossil-derived diesel. Currently, one other liquid fuel that's also coming up is biobutanol. It's not technologically as mature as bioethanol or biodiesel, but it is one of the emerging technologies or emerging fuels. And then finally, we've got biogas, which is also an important biofuel. What I would like you to now know is the feedstock that's being used. So we know for biofuels, the feedstock has to be a biomass resource. Based on the type of biomass that's being used to produce the biofuels, we can classify it under two main categories, either first generation biofuels or second generation biofuels. The first generation biofuels are nothing but where the fuels are produced from food crops, or they are produced from crops that are grown on land that could be potentially used for food crops. So because there is an ethical issue of using the land or the food crops for fuel production rather than food use, it is not advisable. But there is alternative to this, which is a second generation biofuel, second category, which is using the biomass resources which are obtained from waste materials. So lignocellulosic materials for that case are wastes, which are nothing but agricultural residues or forest residues. And in some cases, you can also use municipal solid waste. For producing biodiesel, one can also use microalgae as an option. And then in Southeast Asian countries, people also tend to use palm kernels and jatropha and all those fatty nuts as well to produce biodiesel. In terms of biogas, it is one of the most robust technologies that's been out there for over a century now. And it can handle a lot of feedstocks, with examples being biomass itself or farm waste. We can even use municipal solid waste, sewage sludge. If someone's associated with the wastewater treatment industry, they would be very familiar with anaerobic digestion technology, because sewage sludge is digested anaerobically to produce biogas. And it also simultaneously reduces the sludge volume, which means disposal becomes much easier. And then also food waste can be used as a feedstock for biogas as well. So this is just an example, one of my works to show you an example that biogas can actually make things better. So one of the things that we need to really keep in mind while talking about biofuels is the cost, because if people have to accept biofuels as a technology or a solution to existing fossil fuels, we need to ensure that it is economically viable. The selling price of the biofuels has to at least match the existing fossil fuels, if not cheaper. For that to be achieved, we need to ensure that biofuels are not standalone industries, but operate as biorefineries. And to do that, we've made these techno-economic analysis in one of the papers here that I've mentioned. What we tried doing here was we tried incorporating microalgae biodiesel production process with anaerobic digestion to simultaneously produce biodiesel and biogas in the biorefinery setup to see what the cost could be like. This was done in 2013, so it's almost, it's quite a while ago in terms of these analysis. But what we did come up with as an end solution for this particular work is that the petrodiesel, which is this blue fluctuating curve here, over the years was stable around $1 per liter, $1 US per liter. And with algal biodiesel, if we need to make it competitive to $1 per liter, we could actually make it possible with a biorefinery setup in with biogas complementing the costs. So what we did here was we used a raceaway pond as a system to cultivate the microalgae. Of course, we did use unrealistic algae productivities because we wanted to see if it was even possible to achieve a good enough cost comparison. So we used about 30 grams per meter square per day and 60 grams per meter square per day for the algae productivity. And we also used two options for carbon dioxide sources. One is pure carbon dioxide from cylinders, the other one is flue gas from the coal industry. So we tried using those options. We did not go for a bioreactor because those tend to be really expensive. So we used an option of raceaway ponds, which is nothing but just an open pond with a mixer setup. It's of course constrained by contamination and the algal productivity, but of course there are assumptions here because it's a technical economic analysis. So we've made sure that the assumptions of 30 grams per meter square per day was as much, but not any lower. So we've taken those, and then what we did find out was it is indeed possible to do it this way. One of the important things in this particular work that we did was we tried using simultaneous oil extraction and transesterification step. So in a biodiesel production process, once you've got the lipids in hand, you need to transesterify the lipids to produce the fatty acid esters, which is nothing but the biodiesel. What has been happening traditionally and probably most commonly nowadays as well is extracting the lipids separately and then trying to transesterify it. So what we tried here was we tried to get the proper cost from an existing industrial setup, and then we managed to integrate this in a single step. So the more you eliminate the number of process steps, the more cheaper the process becomes. So we tried combining the extraction step as well as the transesterification step into one, which is nothing but the SOET here. So the algae, once it's grown, it is then mixed with the alkoxide catalyst, and then under cavitation, it actually produces biodiesel straight away without having to go through a separate lipid extraction step and transesterification step. And the sludge produced there was then diverted towards anaerobic digestion, which means it could produce both biodiesel and biogas. So one has to keep in mind that for a biorefinery to happen, there are two important criteria. First being that you need a biomass source to produce the products in the biorefinery. The second one would be that the biorefinery has to produce multiple products so that the prices of the fuel can actually be complemented. So there's a high value product typically which could be sold, and the biofuel can then be maintained at a cost price of the fossil-based fuel. So there can be a good match there. When talking about biorefineries, we also need to understand that there are two terms, linear economy and circular economy. One would be really familiar with what a linear economy is. It's nothing but utilizing a natural resource or any resource for that case, utilizing that in the industry, trying to produce a product, and then you end up with having some waste. And then dealing with that waste for disposal becomes a big hassle by itself. So linear economy is not really the best way forward. So what one has to always think about when thinking about biorefineries is sustainability and circular economy. What circular economy means is you have a natural resource, you tend to use the natural resource or the biomass source to produce a biofuel or other products, and then the waste generated in the process goes back into the loop in the process itself. For example, anaerobic digestion by itself is circular in nature because you tend to produce biogas, which is nothing but methane and carbon dioxide, with methane being the energy carrier. Carbon dioxide has to be stripped off and removed. And the carbon dioxide, when it is naturally taken up by the things like forests or plants, it becomes a circular process because the waste is not being emitted in excess to what's already there in the atmosphere. And then also because you produce fertilizers, what happens there is the fertilizers can go back into growing the plants again. So you virtually end up with a zero waste process, which means whatever is generated in the process goes back into the process loop. And if that can happen, it means it is circular. And I would want to inform you with one of the important definitions of what sustainability is. This was defined by the United Nations Brundtland Commission, and what they meant by sustainability was meeting the needs of the present without having to compromise the needs of the future. what it means that we need to be ethically, economically, and environmentally responsible for what we do today, so that the future generation is not compromised by any means at all. So circular economy for that case is a very viable means to move forward, and biorefineries by nature have to be circular and sustainable. So now moving specifically into anaerobic digestion, I would like you to first know that there are many nature-inspired processes, and anaerobic digestion is one of them. So nature actually, if we try to mimic nature for a few different processes, we could achieve immense potentials, and we could try to also valorize a lot more from nature for that case. So what a cow does is it digests the biomass and then inherits all the nutrients from the biomass. In a similar fashion, what anaerobic digestion does is it takes up all the biomass and gives us important products, which could be in the form of biogas or in the form of fertilizer. The common feature in both these cases is the multiple stages of digestion, both in the cow's digestive system as well as the anaerobic digestion, and also the synergy between a different number of microorganisms that could actually make the process happen. Industrially, the first case that reported anaerobic digestion for an industrial scale was actually way back in 1859. And you'd be surprised to know that India was the first to actually industrially implement anaerobic digestion for biogas production in that particular era. So 1859, anaerobic digestion was first used in Bombay, and it was used to treat sewage sludge to produce biogas and then power streetlights up. So that's a bit of a trivia for you there. So what's happening here in anaerobic digestion is what I'm going to take you through next. In a typical anaerobic digestion process, you have many different kinds of feedstock going in. Like I mentioned earlier, it could be either food waste, wastewater, it could be agricultural crop residues, or even livestock waste like cow dung, as we know. In some cases, animal fats can also go in, but that's not the most common ones that's being used for anaerobic digestion. In India, people would be mostly familiar with the term gobar gas, which is nothing but producing biogas from cow dung. And in industry, it's no different. You tend to use all the feedstock that you have in a digester, which has multiple microorganisms working in synergy in anoxic conditions, which means there's no oxygen present in the system. And any slightest bit of oxygen can actually inhibit or restrict the biogas generation or the microbial metabolic activity. So that care has to be taken really. And then from the anaerobic digestion process, one can actually produce biogas, which is the main product, with about typically 50% of the biogas content being methane. The remaining carbon dioxide, water vapor, and other gases, which could be hydrogen sulfide, nitrogen, and things like that, stripped off, we could get an upgraded biogas, which is almost 90% biomethane, and that is a very good source of energy. One may wonder why methane, being a greenhouse gas by itself, is also a biofuel. So methane is a much more potent greenhouse gas than carbon dioxide itself, but what it has is an energy value, and upon combustion, it tends to produce carbon dioxide, which is a much lesser potent greenhouse gas than methane. So you tend to use methane to produce energy and then emit carbon dioxide. And because the source of the methane and carbon dioxide in this case are plants, what happens here is in a circular economy, the carbon dioxide tends to be absorbed by the carbon sink, which is just natural plants that you have. And because it is naturally occurring forest sinks, it becomes circular economy. So the emissions that we have here will not be a net positive emissions. It will either be net no carbon, which is neutral carbon emissions, or negative emissions for that case. And the second product that we see here is digestate. So in anaerobic digester, you have water, microbes, you have the feedstock going in. The gaseous product that you have is biogas. But what's remaining in the digester itself is the slurry, which is coming off as digestate. Depending upon the type of feedstock, the quality of digestate differs, and the digestate itself can be used as a fertilizer because it is immensely rich in macronutrients, which are readily available to plants, unlike chemical nutrients. So if one has to perform organic agriculture, then the digestate can actually be used as an organic manure, and that could also be potentially useful because you've got a wet content to it, which means the water can also be recycled either back to the digester or it can be used to irrigate the land as well. So depending upon the kind of feedstock, the digestate quality varies, which means the nutrient content of the fertilizer will also vary, which will in turn directly affect your plant growth or influence the plant growth. Now, the digestion process itself and its microbiology. So there are typically 4 stages in anaerobic digestion. The first stage being hydrolysis, which is nothing but breaking down the lignocellulosic biomass polymers. For example, you've got cellulose in the biomass, you've got hemicellulose, and you've got lignins. In some cases, you've also got proteins and fats in excess. So those polymers have to be broken down, and that will be the initial stage in the digestion process. The first stage being hydrolysis, you tend to break down these polymers to monomers, and with the polymers typically insoluble, upon hydrolysis will become soluble in nature. So these soluble organics will then go through a phase called acidogenesis, where a number of bacteria work on these soluble organics to produce volatile fatty acids, and these fatty acids could be higher fatty acids like isovaleric acid, butyric acid, and more than that as well. And the third stage would be acidogenesis, where all of these volatile fatty acids will be broken down to acetic acid. In these 2 particular stages, carbon dioxide and hydrogen are also produced as byproducts, and those are useful in the final stage because acetic acid being the predominant precursor for biogas generation, acetoclastic methanogens tend to use up these acetic acid precursors to produce methane and carbon dioxide, which is predominantly the biogas mixture. And then the hydrogen produced in the second and third stages will be used up in conjunction with the carbon dioxide to produce more methane. So that is performed by a category of microorganisms called as hydrogen-monotropic methanogens. So in a digestion process, you've got a mix of archaea and anaerobic bacteria as well that work in synergy. Because as you know, as biotechnologists, pH and temperature are quite important. So I'll talk about the factors influencing AD in the next few slides, but I just wanted to mention that these class of microorganisms, methanogens, are basically archaea, and the other classes are predominantly bacteria. Finally, in the methanogenesis stage, if there are alcohols being produced, predominantly methanol, that will also be used up by the methanogens, a specific class called methylotropic methanogens, that will be utilized towards methane production. I've got a few names of microbes here, but you can obviously find that in a lot of papers out there. So I don't want to take you through into specific details of each of those microbes, but that's just for you to know that these are different classes that may be present in the digester itself. Now moving on to factors controlling the AD is in the anaerobic digestion. I've mentioned a few different factors here, but all the factors here are related to the first factor, which is the feedstock. If we've got a very simple feedstock like food waste or soluble sugars that's readily available, then what happens is the acid content tends to build up in the digester very, very quickly, which is nothing but you're starting off with the soluble organics directly, and the acid content here will start to just build up right away. So in those kind of feedstocks, one has to maintain a different residence time to actually balance out the acidity of the digester. So if that can happen, then the biogas generation will be much more smoother in nature, the profile of it. And other cases typically, which is nothing but lignocellulosic biomass, you've got polymers in nature. So those polymers will have to be broken down first. And that again also depends upon the residence time you've got. If you've got a very small residence time, for example, bigger feedstocks or complex feedstock like agricultural residues might not be broken down at all. It might be much less efficient to what it could be theoretically. So again, feedstock is very, very important. In an industrial scale, it usually operates about 10 to 15% in solid loading. And it is also limited by the pumping ability as well, because the current industrial pumps can pump up to 25% solid loading in the slurry that you're going to feed in. But otherwise, typically what happens is about 10 to 15% solid loading is good enough to pump into a digester in terms of the feedstock loading there. But what also happens there is the feedstock itself has three main components, which is cellulose, hemicellulose, and lignin. Typically what happens is your lignin and hemicellulose structures will wrap around the cellulose core and create a recalcitrant module. So because this is recalcitrant and difficult to digest, it has to be opened up first, and that is why the hydrolysis step becomes really critical. So for difficult to digest feedstock, hydrolysis stage becomes the rate limiting step, whereas for simple feedstock, the methanogenesis step becomes critical and rate limiting, because methanogens can have a very slow metabolic rate and growth rate, and the doubling times can vary anywhere between a few days to a few weeks. So depending upon the type of feedstock, the balance has to be maintained to get efficient biogas generation. Then, because type of feedstock dictates every other process, firstly, it is the composition itself. As I mentioned, it is important to break down those polymers to monomers. Then, from a microbiological perspective, temperature plays a really important role, because what happens here is for a mesophilic process, as you would know, the temperature is below 40, 45 degrees. And for a tropical country like India, pretty much throughout the year, you can end up operating the digester without having to give in extra energy to heat up the digester, which means there's less energy going into the digester to produce excess energy. So the next case would be thermophilic digester, which is heating the digester up to a temperature of about 40, 55 degrees. And again, thermophilic processes are less complex microbiologically, but they also tend to end up as failures on a longer run, depending upon the type of feedstock. And the slightest of imbalances can fail the digester. So one has to keep in mind that the inoculum composition, or the microorganisms that you have that's working in synergy as a consortia, has to actually have appropriate temperature for it to work. And most common digesters that you would see will be mesophilic. And then finally, one of the growing areas, both in terms of research and basic understanding, would be cyclophilic digesters, because in cold countries where you have to pump in excess energy, say for Nordic countries or European countries where the average temperature in winters is going to be about 3-4 degrees, you would need to even heat up the digester to about 30 degrees to maintain a good mesophilic temperature. The excess energy going in can sometimes be not beneficial, and it will end up making the process net energy negative. So we need to ensure that the energy going into the process is minimal, and the energy that you gain is becoming more, which means your margin becomes more, and as well your revenue becomes bigger. So people are trying to now investigate whether cyclophilic AD, which is nothing but trying to operate the digesters at about 5-6 degrees or its natural temperature during winters, can be beneficial. Again, with methanogens being slow growers and slow metabolizers, its growth is greatly inhibited at these temperatures. So you will never be able to achieve a good enough yield of biogas in the same residence times that you would get with mesophilic, and thermophilic is beyond comparison as well for that case. So those are three different modes of operation for anaerobic digesters. Then would be the retention time, and this is one of the major drawbacks of anaerobic digestion itself, because with complex feedstock going into the digestion process, what happens is you have to go through all these stages, and all these stages have to work in synergy. And typically what happens here is you end up having a residence time of about 4 weeks for anaerobic digestion. And 4 weeks is not very promising for an industrial process. So what people tend to do is go through a pre-treatment step to make sure that the biomass that you feed into the digester is efficiently treated, so that the number of factors can be taken care by the microbes in much more simpler way. I'll talk about the pre-treatment in the next few slides, but I just wanted to mention that retention time is one of the important factors to consider. And then, of course, pH. One might wonder that I've mentioned a pH of 7 to 8 here, but in the previous slide, I've mentioned about acid-producing step. So acid-producing step will actually reduce the pH of the digester. But once you've got a good enough balance, the whole digester or the microbiology can actually operate in the regime of 7 to 8 pH units. So for the methanogens to work really well, you would need a pH of about 6 to 8. And for the acidogens to work really well, you would need a pH of about 5 to 7. And if one strikes a balance properly by getting a steady state really quickly, then you would achieve a pH between 7 to 8 throughout the process at steady state continuously as well. And once that is achieved, you would tend to produce biogas much more efficiently, because pH is quite critical, as it does not only affect the metabolism of the microbes, but it can also vary the fate of different chemicals in the digester itself. And those chemicals can actually become inhibitors themselves. Another one that needs to be considered is the carbon to nitrogen ratio, which is of the feedstock itself. So the amount of carbon to amount of nitrogen will dictate how much of the feedstock is going towards the cell multiplication and how much of it is going towards your biogas generation. So that is critical according to some papers and literature, but what other people tend to do is it is not as critical, because typically in digestion process, what happens is you can never achieve a theoretical maximum. So what happens is, if you've got n number of carbon, nitrogen, hydrogen, and oxygen content in the biomass, you can calculate the theoretical biogas that can be generated from the biomass itself. But theoretically, it is impossible, because you've got a lot of recalcitrant compounds in there. And the maximum possible efficiency is never the theoretical efficiency. So there is a difference between the maximum achievable efficiency in digestion process to a theoretical efficiency of a process. So carbon to nitrogen ratio is critical for some and critical for not so other people. So we don't have to really consider too much or take into detail too much there. But what is important there is the ammonia content. And ammonia content can actually be inhibiting for digesters in the microbiology there. So one has to concentrate on what can be done to avoid the ammonia buildup in digester. Next, the engineering perspective would be the pumpability of the feedstock itself, of course. And it is currently restricted to 25% because of the pumping capability, because we've got slurry pumps that can operate up to about 25%. And these has to be, again, suspended solids. It can't be fibrous materials. So fibrous materials in nature will also restrict the pumpability. So for that case, it is always operated at a lower solid loading rate. Then we've also got the issues with mixing. One would know, if there's not enough mixing happening, it is limited by mass transfer. And mass transfer here, I mean, is the contact between the microorganisms or the extracellular enzymes to the biomass itself. If that doesn't happen, then there's going to be none of the stages that's going to happen as smoothly. So for that case, there are also groups around the world that works on fluid dynamics and simulations to build upon these. And for a continuous digestion process, digestion startup becomes really critical, because in a lab scale, when you want to work on anaerobic digestion, you always tend to work on batch digestion processes, which means you load a reactor with X grams of feedstock, then add X grams of inoculum, and then put it in a water bath to maintain the temperature throughout the residence time, which is about 30 days or so usually. And then you tend to produce the biogas, which you measure and then analyze for different factors. But in a continuous digestion step in industry, what happens is you can't do it in a batch scale. It has to be continuous, because it's a constant inflow of either COD or wastewater or the feedstock supply. So for that case, digester startup becomes really critical. You have to start small and slowly, and then build up to the bigger volume, which can take anywhere between 1 to 4 months to start up. And if you've got a steady state within the 1 to 4 months, then continuous digestion becomes easy, because you just tend to feed in the feedstock at required time intervals, depending upon whatever residence time suits the process. This digester startup time can actually vary between different scales. In a lab scale digester, if you want to do a continuous setup for example, a 2-liter digester, it can be less than a month's time. For a household digester, for that case, it can be between 1 to 2 months. For a large scale digester, let's say about 8,000, 10,000 meter cube capacity, it could be anywhere up to 4 months. And that not only depends on the scale of it, but also on the feedstock. So while I'm going through these, you have now known that all of these factors are actually to the feedstock itself. And finally, the inoculum, which is nothing but the microbiology or the microbes consortium that is going to act on the biomass itself to produce the biogas. So acclimatization is one of the key steps, and that can happen during the startup because you load the digester with some inoculum and then keep adding the feedstock slowly, which means the inoculum there will get used to the new environment and then start digesting the biomass slowly. Synthetic inoculum, I'm not a big fan of it, but that is also one of the areas where research is happening. Synthetic inoculum is nothing but trying to bring in the best of all classes of microbes and trying to build a new consortium or an artificial consortium. It could be extremely beneficial, but it is a very tedious process. So it is always important that one goes towards naturally occurring inoculum. And for that case, cow dung-based inoculum or sewage sludge-based inoculum are always preferred because they've been working in synergy by virtue of nature. So we don't have to really concentrate too much on that side. And another aspect is genetic engineering. One thing that we not mentioned here was use of enzymes to boost hydrolysis, which again is related to the pre-treatment step and the feedstock type. And again, genetic engineering of the microbes for anaerobic digestion especially, I am not a big fan of it either, but that is also happening. And then like finally, I mentioned process efficiency. It could never achieve a theoretical maximum, but there is only a maximum possible efficiency, which is lower than theoretical maximum that is achievable, which is because of the recalcitrant compounds. So because everything relates to the feedstock itself, it is critical that the feedstock pre-treatment becomes an important step in the AD process. So pre-treatment is nothing but trying to break down or access the feedstock, make the feedstock accessible to the microbes in a better way, so that the biogas production can proceed without any inhibition. What are the requirements of pretreatments? If someone's familiar with the bioethanol production process, then they would know that there are critical pretreatment steps there, which needs to be done, because you've got a very common feedstock like a corn stover or a wheat straw or maize or anything like that, which is a polymer insoluble in nature. So an acid hydrolysis and an alkali hydrolysis step usually follows to wash out the lignin or the hemicellulose sugars to get your pure cellulose out. And then the cellulose will be acted upon by enzymatic pretreatment steps, or even just microbes by itself to produce sugars, and then finally a fermentation step to produce bioethanol. But for biogas or for any other biofuel production process or a bioprocessing process for that case, pretreatment has to satisfy these particular criteria. It has to reduce the particle size, because the smaller the particle size, the easier it is for the microbes and the enzymes to act on the feedstock itself, which means it will have an increased surface area, and the amount of sugar release or hydrolysis that can happen in the digestion process will be much more efficient, which in turn dictates the next steps as well towards biogas generation. And then it has to ensure that no inhibitors or no sugar losses are observed during the pretreatment steps, and there are no inhibitor formation. So these are actually the microbiological factors, but there are some engineering constraints as well that one need to really take into account. If we're really talking about an industrial process, the first thing that comes up to anyone's mind is cost, whether it is cost efficient or not, because pretreatment step usually in a bioprocess industry constitutes about 30 to 40% of the costs. So to avoid that cost or reduce the cost, it needs to make sure that the process that we're designing is not only suitable for the feedstock to be treated properly, but also has to be cost effective. Then the process that we design or we opt for has to be feasible in terms of scalability. One can scale up a process or any of the process for that case, but it might not be scalable. So there's no point in just doing lab scale research and then just keep digging into details there, unless we know that there is a way to scale it up properly. Again, scaling up and cost factors are related to the energy efficiency of the process itself, because any of the process that we use as the pretreatment step will require energy or cost for that case. So those are the engineering constraints that also need to be taken into account. And there are 4 main categories of pretreatments, which are physical, chemical, biological, and hybrid treatments. To dig into detail there, this is a typical feedstock here, a fibrous feedstock for that case as an example. What it has is lignin core, which is the red cylinder that I've shown here, with some yellow spots here, which are nothing but the hemicellulose highlighted there. So the hemicellulose and lignin will be interlinked, and they actually encapsule the cellulose, which is the green cylinders that I've shown here. So the cellulose is the most valuable component in the lignocellulosic biomass because it's made up of glucose. It's a glucose homopolymer, so that is the most important component which could be utilized towards any of the bioprocesses, and for this case specifically biofuel production. So the pretreatment categories have to be really efficient to ensure that the biomass is broken down properly. So in physical pretreatment step, what happens is you powder the biomass. That's what you get there, which is a very straightforward process, but is very, very energy intensive, because the energy required for pretreatment physically or trying to grind down the biomass at industrial scale is a very simple technique, but because it's energy efficient, the sizes of biomass that people tend to stop at is actually a lot higher than what is required. For enzymatic hydrolysis or microbiological activity to happen efficiently, the biomass has to be broken down to sizes below 1 millimeter or 2 millimeters at most. But what happens is the lower size you want, the more energy it consumes to produce the particular size fraction. So the energy consumed can anywhere be between about 500 kilowatt hours per ton to about 13,000 kilowatt hours per ton, which is extremely energy intensive. So we need other processes that could take care of the pretreatment step. And there are other steps like chemical and biological. Chemical, for this case, I've shown an example of alkali pretreatment, where an alkali like your lime pretreatment or even sodium hydroxide for that case can act upon the biomass and remove the lignin, which means the lignin less or negligible lignin containing biomass is produced as the product, which is extremely rich in cellulose with minimal content of lignin and hemicellulose. This biomass can then be fed to the digester to produce biogas much more efficiently, because your lignin does not have to be broken by the microbes, but it's already externally removed. So this will improve the efficiency as well. And then similarly, you've got a microbiological process where either the microbes itself, for this case, either a white rot fungi or a brown rot fungi, or even enzymes, can actually act upon the lignin, break down the lignins to produce a similar effect as a chemical pretreatment. Both are really good, but what happens in the case of biological pretreatment is it is extremely slow. Because fungal metabolism is quite slow, it can take a few weeks to pretreat the samples, and pretreating a huge volume of sample or a huge quantity of sample using biological methods at an industrial scale can be expensive, because enzyme recovery is key and enzyme recovery is not as efficient. So for that case, biological pretreatment is not preferred in industrial scale. Then we've got this alkali treatment. It is good because alkali treatment takes lesser time. It is much more efficient in biological process. But again, you've got a byproduct, which is the alkali solution itself. It's coming off at an extreme pH of close to 14, and that needs to be neutralized before disposal. So that adds up additional cost to the whole process. One of the most common ones that's coming up recently is the physicochemical process, which is combining the effects of physical pretreatment and chemical pretreatment to pretreat the biomass. So a physicochemical pretreatment, for example, could be a steam explosion process or could be a cavitation process for that case. What happens here is the physical pretreatment side of the process breaks down the particle size of the biomass or shreds the fibers. And then the chemical pretreatment side of things will take care of hydrolyzing the biomass partially. And that is why I've shown you an example here where there is a fraction of biomass that's floating on top here. And then upon treatment, it becomes a much better turbid slurry. And what this means is the biomass has gone down in size, as well as it has produced some soluble components. And that's why you've got a color to the solution here. What do we typically expect in a pretreatment step? So if you follow the black curve here, what you can see is I've got the arbitrary units in the y-axis here, so don't be confused with what it is. So it could be any biogas volume or specific biogas generation rate or anything like that. So what we see here is with time, the typical biogas generation would be this black curve here. But with pretreatment, we would want to ensure either we improve the rate, which is the blue line, or we have an increased yield and rate, which is the brown curve here. What may also happen is an initial inhibition step, which is the minor lag phase, and then an increase in yield. What this means is the pretreatment step might have produced some inhibitors in solution, which could actually take a while for the microbes to adapt, and then upon exhausting the inhibitors or acclimatizing to the inhibitors, it will start using the biomass. And that is when you see an initial lag there. What we definitely don't want is this red curve here. What happens here is there's no gas production for a few days, and then you tend to produce some biogas here with a much lesser yield compared to your untreated feedstock. What this means is the easily soluble sugars or easily available feedstock is destroyed by the pretreatment process itself, and you also generate inhibitors in addition, which means you're losing out on valuable sugars that can be converted to biogas, and you're also producing inhibitors, which is actually constraining the process efficiency. So these are just typical curves that you would be seeing in literature. And specifically, I would want to take you through a pretreatment step that I'm working on, which is cavitation. Cavitation is nothing but the formation, growth, and collapse of a bubble, microbubble to be specific. So what happens there is once you've got an initial bubble, it tends to grow under negative pressure, and then it will collapse upon pressure recovery to atmospheric pressure or higher. Stopping with the definition there, I will directly now go into types of cavitation. You've got two different types, acoustic cavitation and hydrodynamic cavitation. And acoustic cavitation is nothing but using ultrasound to generate cavitation. So when I'll just show you a small video here. See here is the ultrasound horn that's on top. That is actually pre-treating the biomass strand. Usually it will not be a strand, but a biomass slurry. But I'm just showing you an example here with one strand only, just to show you what the effects are. So you've got the ultrasound horn, which generates ultrasound, and that will actually be transmitting the ultrasound to solution. And with the liquid phase being water, what happens is the vapor pressure of water in the local region drops below, or the local pressure drops below the vapor pressure of water, and then you tend to produce these bubbles. And with continuous compression rarefaction cycles, you tend to collapse these bubbles at a later stage. So initially, you've got the glass strand like that. On 20 minutes treatment, you've got partially broken down strands. And finally, after 40 minutes, you've got pretty much nothing left where the ultrasound was happening. Then the next step is the next kind of cavitation, hydrodynamic cavitation, which is nothing but trying to generate cavitation in a flowing liquid. Acoustic cavitation is good because you can know what effects of cavitation can be observed on biomass, but it is not usually scalable for biomass applications. It's got its own niche applications like surface cleaning and medicinal applications and cell disruption for oil generation and things like that, but it is extremely energy intensive. So hydrodynamic cavitation is an alternative, because what happens here is you're trying to force a liquid through a constriction, which means according to Bernoulli's principle, you tend to lower the local pressure of the water below vapor pressure of water itself. So you tend to produce these bubbles, and these bubbles will tend to grow in the negative pressure, because once you've got a very high velocity after passing through constriction, you will end up getting a negative pressure in the local region, and the bubbles will grow in those regions. And upon recovery of that negative pressure to atmospheric pressure, bubbles will collapse. Once it collapses, what you will have is shear and hotspots. The shear will pretreat the biomass physically, and the hotspots will cleave water to produce oxidizing radicals. And these radicals will tend to hydrolyze the partial fraction of the biomass, which means your biomass is actually pretreated both physically and chemically. The common devices that people report in papers are nothing but orifices and ventures. Orifice is nothing but a plate with a hole. So you've got a plate with a very small hole, and you pump in the biomass slurry through it, and you generate cavitation at the hole here, and this can break down the biomass. Similarly, venturi is nothing but two inverted funnels joined together as an example I would like to show you there. But what happens again here is you've got a small construction. When the area goes down with a particular flow rate, your velocity tends to decrease and you generate cavitation. One of the important disadvantage of both these devices are you tend to erode the device itself because cavitation is damaging. So in an industrial scale, you can't afford to have that, which means you need to continuously maintain the equipment very frequently. And again, because we're dealing with biomass here, it can tend to clog these the holes. And the construction sizes that we're talking about is in the range of millimeters. So it could be around 2 to 3 millimeters mostly for industrial scales. And for that case, if we have fibrous biomass, which are typically about 20-25 millimeters long, it could easily clog up the pores, and then it might not be as efficient. So again, maintenance becomes key. So it requires a definite pre-milling step, which means milling the biomass itself will ensure that flow or pumpability is maintained through these devices. But then what we are trying to do is not use these devices and have a novel device called a Vortex diode, which works on the basis of a swirl flow. I don't want to go into details there too much, but what it means is it has the same effect as other cavitation devices, but it's got a lot more advantages to it. For example, it's got no small holes. It can generate cavitation at a very lower energy input, much lower energy input. And then the cavitation collapse, which means the bubbles that are produced collapse outside or far away from the walls, which means they are collapsing in the core of the flowing liquid, which will not erode the device itself. And again, the yields are much better compared to linear devices. So we've been using this, and continuous and lab scale experiments. What we usually set up is like this. On the left hand side, we have a batch circulation setup, which is nothing but you've got the device here and there's a holding tank. So it just keeps looping through the device until the number of passes that we want. Number of passes is nothing but the amount of the number of times the total liquid in the holding tank goes through the device. So it is critical we do it on the basis of number of passes, but not on time, because time could vary depending upon the volume that you do. So time can't be a parameter to compare here, but number of passes in this case. For industrial scale, what happens is you can't really have a holding tank here to keep doing this. So we continuously send the biomass upon pretreatment. And we have been successful in scaling up this as well. And I'll show you an example later on. So what happens here in this case is there is a net flow to the digester, and it flows through the device here, which means we control the ratio of the flow rates to the device and to the digester itself, which gives us a number of passes that's required. By maintaining this number of passes as a factor, we can pretreat the biomass efficiently. The challenge is, again, I don't want to go too much into detail here. I'll directly go into a biorefinery example. So this is one of the biorefineries that we are working on currently. What we try to do is we try to use sugarcane bagasse, or the stems of sugarcane, and then pretreat that using cavitation to enhance the biogas outputs, and then use digestate as a feedstock to produce other products in the biorefinery. So where we use cavitation in this case is these two process steps. The first one being the pretreatment for anaerobic digestion, and then the post-treatment of the digestate to extract sugars or cellulose out. One of the examples here, we've got a paper published on this site, so if you want to know more details about this, you can take a look at the paper there. So the black spots there are nothing but the untreated bagasse that we have, and upon cavitation pretreatment, we do see an improvement, and with 9 passes pretreatment, as I mentioned. Like we were discussing earlier, it is critical that the energy requirement for a pretreatment step is small, so your margin can be improved better. What we've done here is, for this particular case where we've seen an improvement, we've used this as an optimized condition and then simulated the costs or the energy required for pretreatment for the industrial scale. We could see that the energy requirement keeps decreasing with an increase in solid loading, assuming that the energy gain stays the same, which will not be the same industrial case. Actually, it could fluctuate between a certain range, but it can never be much, much lower than what we see here. So at this particular spot is the lab scale that we operated, and we can see it's already an an energy gain, a net energy gain that we see here. And this margin keeps improving once we keep increasing the solid loading. When compared to other processes, we can see acoustic cavitation is much higher in terms of energy consumption. Physical methods is nothing but milling that we saw about earlier, which is also higher. And conventional devices, which is nothing but the orifice and venturi, are also higher in terms of energy consumption. So what we could actually do is we could design a process which is much more energetically favorable and could improve the margins in biogas generation, which means the biofuel production process can be cheaper, and then the existing digestate that we produce can either be used as fertilizer or could be diverted towards other products as well. This is another example with a distillery wastewater, or spent wash as it's known as. Distillery wastewater has got alcohols and residual sugars, which means they're easily utilized. And what we see here is there's an overlap of both the untreated and pre-treated samples, which means the easily available sugars are not lost due to cavitation. So they are retained in the process, but the recalcitrant feedstock is actually broken down to a much more simpler feedstock. So we see a much smoother biogas generation profile in the green squares there. With the black squares, which is the untreated feedstock, what happens is you tend to produce biogas in two different stages. That is because you've got complex compounds in the wastewater that needs to be broken down. So the simpler compounds go off first, and then the partially complex organics will be broken down to produce biogas, and then a minimal lag happens, and then it continues again. So this complex biomass that we see here in this case is broken down with cavitation pretreatment, and then we tend to again improve the biogas production here. In this case, only 2 passes. And in an industrial scale, we've managed to do it with just 1 pass only, which is just sending it through the diode once. And we can see the energy difference becomes bigger once we improve the solid loading, or in this case, the COD loading. And on the right-hand side, if you can see, we've got the industrial data. So we've managed to scale it up for industrial scales here. Flow rates ranging between 13 meter cube per hour to 50 meter cube per hour. And then we can see we could get similar increase in biogas yields from 10 to 22%. And again, we've got this published recently as well. So if anyone's interested, feel free to take a look at the paper or come back to me. So what I've shown you here is the potential of bioenergy to supplement the transportation fuels and the gas grids. And one needs to also keep in mind that anaerobic digestion is a good technology. It can be a promising biorefinery platform in itself, but the acceptance again depends on the cost of what the end product is. Biomass valorization is key because if one has to move towards circular economy and be sustainable, biofuels are one of the way forward, and hydrodynamic cavitation is one of the things that we work on, is an efficient pretreatment method that could make this happen. And finally, thank you very much for your attention, and I'd be happy to take any questions. Got a question from Balakrishnan Arjunan. He's asked, the biogas is composed of carbon dioxide, hydrogen, and nitrogen. Biogas is a predominant composition. The predominant composition of biogas is carbon dioxide and methane. You will also have traces of hydrogen, nitrogen, and hydrogen sulfide in some cases as well, and very minimal oxygen, and water vapor depending upon what temperature you operate the AD at. Do we have any other questions? Okay, we've got, will biogas fulfill the energy needs? That's a very vague question. I'm not sure what energy needs they mean by there. Kannadasan has asked, in comparison between plant-based biogas and microbes like algal-based biogas, which is most preferable if one decides to start up an industry? You can't really outrightly compare it that way because you've got a lot more constraints to it. For example, for algal-based systems, you would need to ensure what type of algae you're using, its productivity, and things like that. If you're trying to use seaweeds or macroalgae for that case, you would again need to know the productivity of it because the composition of seaweed is better for biogas generation because you've got cellulose and hemicellulose with lignins there, and there are problems associated with it. And lower cellulose content is also beneficial sometimes when you have a higher lipid content in case of microalgae. But again, what happens there is microalgae, it's difficult to grow on a larger scale with big productivities. So it needs to be really a balance between what you would want to do. But in terms of starting up things quite easily, it would be the municipal solid waste and local agricultural residues. So biomass or plant-based would be the easiest ones to start off with. Just trying to scroll some questions there. What is the most cost-efficient method used presently? What percentage of biogas energy is currently in use? Yeah, India, on an industrial scale, we don't have as big biogas setup. So currently, what the government is trying to do is they've introduced a scheme called Satat, which is Sustainable Alternative Transports Scheme. So what they're trying to do there is they're trying to subsidize industries and they're trying to call in companies to start up biogas plants based on biomass resources to build base. So they're trying to fund about 5,000 plants in the next few years to ensure that the biogas capacity in India is greatly increased. So they're trying to even give a buy-in price of 46 rupees per kilo of compressed biogas, which is nothing but methane content of higher than 90%. So that is really important, and I think India is going in the right direction for that particular side of things. So that is a very good initiative, and there's been a very good response for it as well. And the first call was over in 2018, late 2018. So there might be a few more calls coming up on that side. So industries are actually taking full leverage of it. So that is one of the things that I wanted to mention for this particular question. Again, Balakrishna Arjunan has asked how much megawatts can be produced in India with the help of sugar mills. I don't have the number at the particular moment now off my head. I can pass it on to the organizers if you're really interested. I've got it somewhere in the computer there. And he's also asked, energy plantation provide fuel, wood, charcoal for rural employment? Yes, it is a very good chance for rural employment as well. Because what happens here is the logistics of it will create employment. Because if we're talking about agricultural residue, once the harvest happens, we get a lot of agricultural residues which are not utilized for a lot of resources. So if the logistics of it can happen, it will actually fetch more money to the farmers themselves because the crop prices being not so much, and there are a lot more problems associated with the farmers' crop produce and the price that's being paid to them. If one can actually utilize biogas generation as an alternative to the residue that they produce, what can happen is it will actually improve the value for the product for the farmers. It will create a job employment in the logistics sector where it can actually help in transporting the feedstock to a centralized area where the AD can actually happen. And then operating the AD, of course, will be generating jobs as well. So waste mitigation and energy generation is one of the key areas in the future which can actually generate a lot of jobs. So Mukesh Kumar has asked, what are the measures to be taken to create awareness among people about biogas? Basically, just keep educating people. If you just even speak to people next to you, I mean, not necessarily it has to happen through conferences. It can even happen through one-to-one talks as well. So keep educating people about bioenergy. Keep educating them about the awareness. Keep creating or organizing sessions to open publics. One of the things that India is lacking currently is open public talks. So scientific talks tend to always happen within a community, a closed-gate community, but there has to be public outreach of scientific innovations or even basic sciences for that case. And things like those will actually be helpful in creating awareness among public. If one can actually go talk to public, create awareness that way, that will just keep on multiplying, and that's the only way to do it. And changing people's mindset is one of the most difficult tasks, and it has to happen throughout in any era. It shouldn't stop, and it just should continue. Lavanya has asked, electric cars are coming into use, which would be more advantageous, electric or biofuels? Again, electric cars are coming into use, yes, but it depends on the source of electricity. If one is producing a coal-based electricity and then using it to power cars, then if you consider the whole life cycle of it, it is actually going to be net carbon positive, which means you're emitting carbon dioxide in the life cycle of the whole process. But if it is coming through a biofuel generation process, then it might not be carbon positive. So you have to again see what is the source of electricity there and then compare it. Mukesh has asked, how eco-friendly will be biogas then compared to other resources? I would say probably biogas is one of the most eco-friendly processes that you can ever actually have in terms of comparing current processes of renewable energy technologies. Because for a solar panel-based work, or even for your wind technology or wind energy-based technologies, you tend to produce all those panels and windmills and everything based on products that come from fossil-based energy. So the return of investment for that case, or the energy neutrality to achieve, it takes a while. But for biogas, because you are actually asking the nature to take care of it, which means the plants coming in as feedstock produce biogas, and the carbon dioxide goes back to the plant's photosynthesis, which produce more plants again, and the fertilizer that you produce can be fed back to the the fields to grow the plants again. So it's a circular process, and it's probably more eco-friendly than other process. Vani is asked, cellulose-based biofuel production, does it have future research? Yes, cellulose-based biofuel production is the way to go forward if you're talking about bioethanol production or biobutanol production for that case. We've got a lot of industries in India that do it, and in Pune there's one called Praj Industries, which is a very specific one, and they are a global leader in second-generation bioethanol pretreatment process, and they've actually been having very good links with all over the companies, a lot of companies globally. So yes, cellulose-based biofuel is a way to go forward. And if you take a look at countries like Brazil, for that case, bioethanol is their way of living. So they are one of the most successful countries that have been using bioethanol as a fuel supplement, and also in mix with petrol to move the transportation sector and keep it going. They've actually been focusing on sugarcane juice as the feedstock, but what is also happening is they're trying to move towards second generation biofuels using sugarcane bagasse, which is the waste resource. Have we got any questions? There's also one other question which has been asked by one of the attendees. So, is biogas? Is there any specific container to store biogas? No. What happens is, in an industrial scale, you've got big balloons, analogous to big balloons that store the biogas. In lab scale, you've got Tedlar bags that can do it, and otherwise, it's pretty much just cylinders that people compress them in once you've got the proper content, what you want, or composition of what you want. And if there are no more comments, I think we can finish there. I think, yeah, we've got no more comments. Yeah, we should be okay to finish, I think. Yeah.
Can you hear me, right? Sanjay?
Yeah.
Actually, very informative session. You talked about a lot about biofuels, not only the advanced papers like management perspective, but also the basic principles that is need to be taught for biofuels, biogas especially. And I think a lot of the participants agreed with you, what I said. They said that it is very informative, very simple points of everything that you put in everything. And I believe that session has been useful for others as well. And the link, the video recording will be available in YouTube. I'll send it to the participants for the others. And there are, if they need any other doubts on the sessions, they can contact through me, something like that.
Yeah.
And I want to thank you for this wonderful session from you and spending your time. I know you are busy and you have a lot of other works to do. And I want to, on behalf of the department, on behalf of me, on behalf of the college, and I want to thank you very much.
Yeah, thank you very much for that as well. It was great pleasure talking about biogas and what I do as well to a few other people who are not aware of what's happening. And I'll be really happy to come back and do something of this sort again as well. Thank you very much for having me in.
So we can end this session here. Thank you, Sanjay.
Thank you.